All right. So any specific ones you want me to go over? Matt,
5.
number 5.
Did we all miss five?
With the drop ball? On the assignment that I just gave back, or is
Oh,
one
something
for
you just
today?
gave back.
What's number 5?
Taking the direction of the initial motion to be positive.
Okay.
The slope of the velocity time graph of the body moving in a straight line is negative.
So here's the velocity time graph, okay? So let's say you're moving at 10 meters per second. So it's going to do one of two things. By the way, for those of you that are watching, this is on assignment 3-1 that I just gave back. So this isn't on today's assignment. So if it's sloping upward, okay, it's going to be speeding up. If it's sloping downward, you're going to have negative acceleration and you're going to be slowing down.
Okay. Well, yeah, I mean, I understand why I'd be slowing down. I just don't understand why my answer C, acceleration decreases with time.
Because
Oh, wait,
you
got it.
always have uniform acceleration, okay? It's a straight sloping line, that's the whole point.
That makes sense.
Yeah, don't
Velocity.
confuse, again, don't confuse acceleration with slowing down or speeding up, okay?
Yeah. I
Hello?
got mixed up with velocity.
Thank you.
See, I think I was looking at the ones and I was like, the slope is
I was like, if the
acceleration.
slope is going down, then no matter what, it's decreasing with time, no matter what. Like the magnitude may be increasing, but the actual number is decreasing. If you-
Okay, now let's talk about the assignments due today. Any questions on that?
No, not so far.
Well, let me go over some ones that are notoriously missed, okay? So let's talk about this one on, which one is it? The one with the kangaroo. Where's the one with the kangaroo?
8.
Huh? 8, there it is, I was in front of, okay. So here's a horribly drawn kangaroo, okay, right?
I can guarantee you minus worse. I
Huh?
did a stick
So
figure
I just
with
wrote
ears.
It's not a bad kangaroo, I've drawn worse.
Mine is a stick figure with ears.
Okay, I can live with that too.
Mine looks like a
Okay.
Tasmanian dinosaur.
I didn't. I said
So here's the idea, right? So on this one, he's going to jump up to a height of 1.5 meters. So 1.5 meters would be about like this tall. Okay, it's a fairly decent jump. So again, if you look at what's happening on number 8, you don't have time, right? So the idea being is that this kangaroo is going to jump up with some initial positive velocity. And that as that kangaroo goes up, that velocity is going to become smaller, okay? So if your velocity vectors are becoming smaller, that means you're going to have an acceleration vector that's going to point in the opposite direction. So in this case, I'm going to have some negative acceleration. So that's all you have to have on 8A. This is all you have to have. A couple of velocity vectors pointing up that are getting smaller, one acceleration vector pointing down that's getting smaller. So then, on this one, then you want to know, okay, with what velocity did it leave the ground? So you don't have time, right? So just go, oh, v squared equals v naught squared plus 2ad. So here's the whole key to this thing. You're searching for the initial velocity, okay? This is the one that you don't know. Now, when the kangaroo gets to its highest point, what's the final velocity going to be? 0. So you're going to go from some initial velocity to 0, and you know the acceleration. So this is what, no, it's vital that you solve for v naught. Oh, so that's going to be v squared minus 2ad, and the square root of all of that is going to get you v naught. So this is why you have to work this in terms of sign, and you have to be consistent. So that's going to be 0 squared minus 2 times negative 9.8 meters per second squared times 1.5 meters. Okay, and then don't forget to take the square root. So this is why you have to have this negative minus a negative value underneath this radical so that you don't end up with a negative, with an overall negative value underneath that square, and then you get like imaginary velocity, and that just gets weird. So anyway, so your answer to number 8 should be around 5 meters per second. Okay, and notoriously what you do is you forget to take the square root of all of that. Your answer to number 9 should be in the mid-30s. Your answer to number 10A should be around 30. Now, let's talk about number 12 and what I'm looking for on number 12. So, number 12 is kind of similar to what's going to happen on number 8. You're trying to figure out how fast you have to throw this rock on the earth to get to a height of 25 meters, which would be about 10 times the height of this ceiling. So that's a pretty good toss, right? So then you're going to go to the moon, and the whole key to this is you're going to throw it with the exact same velocity. So, because if your answer to 12A is wrong, everything else is going to be wrong. So your answer to 12A should be around 20-ish, okay? That's an ish, but it should be something around 20. So what I'm looking for on that velocity time graph that you're going to draw, you're going to say, okay, this is going to be this initial velocity, which is going to be around 20. And you're going to go, okay, this is going to be my earth line, okay? So this is going to have a slope of negative 9.8 meters per second squared. The whole key to this then is you're going to go to the moon and you're going to throw it with the exact same velocity. Now think this through. If I go to the moon and I throw this golf ball with the exact same velocity that I do right now, what's going to happen to the height that it's going to go to? Yeah, it's going to go up quite a bit because of the fact that I'm going to throw it with the same velocity, but it's not going to slow down as much after it leaves my hand. So it's going to go to a higher point before it starts to come back down. So you got to figure your answer to 12B is going to be bigger than 25 meters because it's going to go to a higher point. So you should have, on this velocity time graph, you should have 2 lines, okay? Make sure, you don't have to find the exact times, but this is just, hey, do you understand what's going to happen? So label that with, make sure I know which one is the moon line, which one is the earth line. Yes?
I did have a question for 5C, where you're finding the distances. I kept getting negative, which I know you can have a negative distance, but you can't have a negative for like relative to the reference point, right?
Yes, you can.
Okay.
You can have a
Well, like I'm thinking like you can't go negative distance.
No,
Always moving, but
no, okay.
relative.
This is displacement,
Okay,
okay, which is a vector quantity.
okay.
So on number 5, that's one with the bridge, okay? So all we're doing is we're calling the point that you let go of it, we're just making that 0, okay? That's it. So we could make these positions going down be negative values, or we can make them be positive
Okay.
values,
I
okay?
was just clarifying.
But just so that we're consistent, because down is going to be negative, because you're going to have a negative acceleration. So therefore, hey, in this problem, we're defining down as being a negative value. So yeah, so you're going to go like down to -1, -2, -3, -4. Now, if you were to throw it up in the air, it would go from 0 to +1 to +2 to +3. Yeah, you can have negative displacement, you can have negative acceleration, you can have negative velocity.
Okay.
Okay?
So you said number 9 was around 30 or whatever? Is it around negative?
No, well, that was just the value.
But it's negative?
Yeah.
Okay.
Yes, that was just the number.
I didn't know that either. I was like, you can't have negative distance, but I figured it out.
You can't have negative distance, you get negative displacement.
Yeah.
Yeah.
Which is, okay, yeah.
Yes. Okay? Now, let's talk about that last one on number 15. Okay, even though you haven't asked about it, let's talk about number 15. So, speaking of a bridge, so you've got Leroy and you've got Bubba, and you've got Daryl, okay? So, I won't use I'll use a golf ball instead of a bowling ball. So here's the setup, okay? So, Leroy just drops the bowling ball, right? So here's this velocity time graph. And Leroy is here, and he just goes, yeah, screw it, and just drops it. So where's Leroy's graph going to start?
0.
0. And what's the slope of that line going to be?
Negative 9.80 meters.
Negative 9.80 meters per second squared. Okay? So there's Leroy's line, right? Okay? Now, then, Daryl throws the bowling ball straight up. No, Bubba throws it straight up with 10 meters per second. So Bubba's going to do this. He's going to do that. So that's going to be that motion, right? Now, here's the difference. Leroy just drops it. Does his bowling ball ever change direction? No. Now, Bubba's, does his ball change direction? Yes, so his ball has to cross through 0 meters per second. So Bubba is going to start up here at 10 meters per second, but as soon as he lets go of it, what's the only force acting on it? Gravity. Gravity is the only force acting on it, therefore you're going to have the same slope. So that's going to start at 10 meters per second, and then it's going to slope down like this. Okay? So, where am I? Hold on, I need to get one thing. Where did it go? So we'll talk about this concept. It's called Jedi Stoffel law, okay? And the Stoffel law stands for stop the force and watch, okay? So, and this will play out large once we get into forces, oddly enough. So, if you look at this in terms of Stoffel law, so as soon as it leaves my hand, if I throw it up in the air, if I stop the force from my hand, and I watch what's happening, the only force acting on that ball is gravity. It's going to make it slow down. It's going to have the same slope as this one does. Now, then you have Daryl, okay? Daryl has anger issues. Daryl says, oh, screw it, I'm going to throw the ball straight down. Now, so Daryl is going to start at negative 10 meters per second, but he's going to throw the ball straight down. So, does his ball change direction? No. But again, even though he throws it straight down, as soon as it leaves his hand, what's the only force acting on it?
Gravity.
Gravity. So guess what? All three lines are going to have the exact same slope. Okay? At negative 9.8 meters per second squared. But this one is going to change direction because it's going to go up and then it's going to fall. Because if you think about it, this one, when it starts to fall, is the exact same motion as Leroy's was, okay, when it changes direction. But you can find this area and go, oh, that's how far it's going to go up before it changes direction. Then you got Leroy's, and then you got Daryl's, so you're going to have all three lines that are going to be parallel. Okay? Because once you let go of it, the Jedi Stoffel law, stop the force and watch. Once it's let go, the only force acting on it is gravity. Okay? Cool with that? Anything else you want me to go over on that assignment? Let me give you one other hint. On number 14 with the pyrotechnic, your maximum height on number 14A should be around 130. And that velocity at the end of 5 seconds should be a very small positive number. Okay? A small positive number. Okay, we're good? Going once, going twice. So, okay, so here's what we've got today. We have one big problem left to work, and then I'm going to turn you loose on a lab. And then that'll be due tomorrow. We'll review tomorrow, then big test on Friday. So Friday's the first really big test. All right, so here's what we're gonna do. So I'm gonna take this ball, and I'm gonna throw it up in the air, and I'm gonna keep track of how long that ball was in the air from the point that I let go of it until it returns back to my hand, okay? So I'm gonna throw this ball up. Oddly enough, hopefully it comes back down. And the whole key to this is that we're gonna return back to the same point that it's launched at, okay? And let's say that my total time was 2.80 seconds, okay? So from the time that I let go of it until it lands back in my hand, 2.80 seconds. That's the only number that I know. So from that, I want to determine my initial velocity, okay? I want to find the maximum height, okay? I want to draw a position time graph. I want to draw a velocity time graph. I don't know why I'm putting question marks on the end of those. And then I want to know the height at 1 second. I want to know the velocity at 1 second. I want to know the height at, what was time? Okay, so here's the deal. So we only know one number. We know the time, right? So the time that I let go of it until the time it gets back in my hand is 2.80 seconds. So I want to find the initial velocity, the max height, draw the position time graph, the velocity time graph, height, velocity at 1 second, height, velocity at 2 seconds. So now what you'll see is if you screw up the initial velocity on this problem, everything else is going to be wrong, okay? So it is absolutely vital that you get the initial velocity right, or everything is going to be wrong, okay? So here's the deal. Let's actually start with the position time graph. So Shivani, what's my position time graph going to look like? Something like this,
Yeah,
right?
yeah,
Is that what you meant?
yeah.
Okay? So the total time is 2.80 seconds. So how long is it going to take to get to that maximum height then?
1.4.
Beautiful. Okay? So my maximum height is going to be at 1.40 seconds, because what we're going to assume, and this is important, what we're going to assume is that this thing is symmetrical. And we can do that as long as you come back to the same height. Okay? Now, if I do this where it falls all the way down to the ground, like we'll work tomorrow, completely different problem. Okay? But if I throw it up in the air and it comes back to that same height, this thing is symmetrical. Time up is going to be the same as the time down. Okay. So, Kara, what's my velocity time graph going to look like?
Speeding up at the slowing down at the beginning, and then it speeds up on the way down.
Okay.
I'll explain it. You know.
So we're going to look at it from the point that I let go of it until it returns back to my hand. So, is it going to start at 0, or is it going to start up here at some positive value?
It starts at 0. No, it doesn't. 0 is when it's changing direction.
Yes. So it's going to start at some positive value, which I don't know, right?
Mm-hmm.
And it's going to do what?
It's gonna, cross
Just
the-
straight sloping down like that. Because gravity is going to provide the force, so that's going to provide the same acceleration, right? Okay? So we got that, right? Now, this is going to be 1.40 seconds, okay? Now, did I give you the mass of the ball? No. Why? Why did I not give you the mass of the ball?
It doesn't matter.
Doesn't matter, okay? Look at every equation that you've dealt with so far, okay? There is nowhere to plug mass into that equation, okay? So whether I launch a bowling ball or whether I launch a golf ball, it doesn't make any difference, okay? Mass is not a factor. It's not there. You can't plug it into the equation if you try. Now, would it be harder to throw a golf ball, or excuse me, a bowling ball up in the air? Yeah. But after it leaves, the only force acting on it is gravity. You're going to get the same acceleration. So this is why I'm never going to give you the mass of anything right now, because it doesn't matter. Now, when we deal with forces, it will matter. But right now, I am not going to give you the mass of anything on any assignment or on the test or anything, because it doesn't matter. It's not a factor. Okay. Now, Kara, what's the slope of this line going to be?
Negative 9.80 meters per second squared.
Beautiful. Okay? Now, let's talk about that initial velocity. Miss Pfeiffer, is that initial velocity here going to be bigger or smaller than a positive 9.8 meters per second?
On the way up,
Yep, on the way up. Is my initial velocity going to be bigger or smaller than 9.8 meters per second?
it's gonna be bigger because it's 1 in a second.
Beautiful. Fantastic answer, okay? Because if the initial velocity had been exactly 9.8 meters per second, if it had been exactly 9.8, it would have taken exactly 1 second to go to 0, okay? So since it took more than a second to go to 0, I know my initial velocity has to be bigger than 9.8, okay? It's like if you go with the money analogy. Oh, I have to spend $10 per second. It took me 1.4 seconds to run out of money. Oh, therefore, I had more than $10 to start with. Okay? All right. So, let's chit-chat. So let's talk about that initial velocity. So Matt, on the way up, my initial velocity is what I don't know. Okay? But what's my final velocity going to be?
0.
So on the way up, V naught is my unknown. But I know my final velocity is going to be 0 meters per second. Okay, that's kind of cool, right? Okay? And then if you look at dat, I also know my acceleration, because that's going to be negative 9.8 meters per second squared. Okay? Now, how long is it going to take to get to that final velocity of 0?
1.4 seconds.
1.4. It's going to be half the time, right? So I also know my time, which is going to be 1.40 seconds. Okay? So, Matt, I need an equation that relates acceleration time, initial velocity, and final velocity.
You can use V equals V naught plus acceleration times time, which you can move around to V minus.
Beautiful. So I need to isolate this thing for V naught. So what am I going to do?
Subtract 18.
So I got V minus at equals V naught. And again, you have to work this thing consistently. So I'm going to have 0 minus a negative 9.8 meters per second squared times the time of 1.40 seconds. So Matt, do us a favor. Take 9.8 times 1.4.
13.72.
So 13.7 meters per second. Okay? Now, that matches with what we said. Okay? Lee said, hey, that velocity has to be bigger than 9.8 meters per second. And it was. Oh, okay, right? It's going to be a positive number. So what that means is if you go back to what we started with the position time graph, if I were to come in here at time 0 and draw that slope of that tangent line, that would have a slope of 13.7 meters per second. So this is why we knew, okay, hey, this is going to start at 13.7. Now, this is where both graphs have to show the same thing happening at the same time. So this graph here is going to start at 13.7 meters per second. So as soon as it leaves my hand, this velocity is going to decrease, which is why this position time graph, which is what Shivani just said beautifully, oh, it's going to be this parabolic curve. Because these lines are going to become less steep. because this thing is slowing down. I got a decreasing velocity. My position time graphs are becoming more shallow. Those tangent lines are becoming more shallow, okay? Now, at this point at 1.40 seconds, this is when the velocity goes to 0. Oh, I have a tangent line of 0. That's when this graph goes through 0 meters per second, okay? So this is why you have to realize, oh, both graphs have to show the same thing happening at the same time, okay? Cool. All right. Now, we got that done. Now, if you really want to make sure that this is right, okay, here's what you can do. Treat this as your initial velocity, find your final velocity, which is going to be 0, divide it by 1.4 seconds, see if you get an acceleration of negative 9.8 meters per second squared. Because literally, if this number is wrong, everything is going to be wrong, okay? So yeah, I'm just telling you, you might want to double check and make sure that that answer is correct. Or you can take 0 minus 13.7 and divide it by negative 9.8, see if you get 1.4 seconds, okay? That's the other thing that you can do. You don't have to, but if you really want to make sure that you're right, that's what you can do. Okay, so we got that. So now we need to find the maximum height. Now, there's like 3 different ways you can find the maximum height. So, what's one way that I could find the maximum height? So I've got this nice velocity time graph. How can I use my velocity time graph to find my maximum height? Karen?
P equals 1/2 h.
No. I just want to use my
Oh.
velocity time graph.
Oh, can you just find the slope? No.
No, we know what the slope is.
That equation?
Nope. I want to use this graph. What's this shape look like?
Triangle.
Oh,
So find the area.
yeah. Do I know the height of the triangle?
Yeah.
Do I know the base of the triangle?
Yeah.
Oh, I can do that, right? Oh, it's like, oh, I like triangles, Mr. Brickout. Happy for you? Okay. So, one option is that I could just find this area. So I could go area equals 1/2 base times height, right? So that would be 1/2 my base, which is 1.40 seconds, times that 13.7. So Matt, take 0.7 times 13.7.
0.7 times 13?
Yeah, 0.7 times 13.7.
Oh, 9.604.
9.60 meters. Okay? So that area is 9.60 meters. That's my maximum height. Now, it's like triangles have always kind of flipped me out. Okay? All right, well, let's do something else. So how else could you find the maximum height? Carrie, you ran some off. I could use that equation, right? Okay? So I could use that equation. I could go v squared equals v naught squared plus 2ad. Okay, if you like that equation, you can use that. Oh, okay. So that's going to be v squared minus v naught squared over 2a is going to equal my distance. So I have 0 minus 13.7 meters per second squared divided by 2 times negative 9.8 meters per second squared, and you're still going to get 9.60. Whoa, come back here. And you're still going to get 9.60 meters. Now, there's a third way that you could do it. You could use distance equals 1/2 at squared plus v naught time. You could do that. Now, here's the question. What value of time are you going to put in here to find the maximum height? Are you going to put in 1.4 or 2.8? 1.4, because that's when it's going to be at its maximum height. Okay? So you could come in here and you go 1/2 negative 9.8 meters per second squared times 1.4 seconds squared plus 13.7 meters per second times 1.4 seconds. Okay? You could do that. All right? So how you get your maximum height, I don't care. It's a personal preference thing. Okay? You just have to pick the one that makes the most sense to you. Now, here's what's important though. Notice that all of them, to find that maximum height, they all depended upon that initial velocity of 13.7 meters per second. That's why I said if that number is wrong, everything else is going to be wrong. So that's why it's so critical that you get that initial velocity right. Okay. Now, I want you to listen very carefully to what I'm about to ask you. So it launches at 13.7, it goes to 0. Now listen to me very carefully what I'm about to ask. What's the velocity of the ball when it lands?
Negative 13.72.
Negative 13.7. So the slope of this tangent line over here would be negative 13.7. So the velocity when it lands would be negative 13.7 meters per second. Okay? Now, what's the speed of the ball when it lands?
13.7.
Yes, because speed is just a scalar quantity. So if I said, what's the speed of the ball? Oh, it launches at 13.7, it's going to land at 13.7. So the speed, which is just how fast it's going, is the same. The velocities are not. You're going to have the same magnitude of 13.7, so the slope of this tangent line would be positive 13.7, but the velocity here would be negative 13.7. Okay? So that's what I want you to see is the difference. So you have to keep straight the terminology. Speed is just how fast it's going. Hey, 13.7, 13.7. Velocity, though, would be positive 13.7 and then negative 13.7. Okay? So, Matt?
So like when you ask how fast are you going, do you want us to assume you mean velocity or speed?
Yeah, you can't never go wrong with velocity. Okay? You can never go wrong with velocity. Okay, so we have one calculation left. Actually, two left. So we need to find the height and the velocity at 1 second into the flight. Okay, 1 second into the flight. So at 1 second into the flight, is the ball still on its way up or is the ball on its way down? How do you know?
It's turning at 1.4.
Yeah, it reaches its maximum height at 1.4. So at 1 second, it hasn't reached that point, so the velocity is still on its way up. Okay? Now, so the easiest thing to do to get that, and there's only one way you can do that, is to go, oh, okay, V equals V naught plus AT. And again, this is just a slope intercept. You're starting at 13.7 meters per second, okay? That's my initial velocity right here. 1 second later, it's dropped 9.8, okay? So that's all this is. Oh, 1 second. Oh, it's dropped 9.8 meters per second. So all you have to do is subtract 9.8. So you're just going to go, okay, 13.7 meters per second plus negative 9.8 meters per second squared times 1 second. Matt, take 13.7 minus 9.8.
3.92.
3 point what?
9. 2, but...
Yeah, 3.9 meters per second. Now, here's what that means. Okay, and this is like the magic code. If I said, hey, go to the position time graph and at 1 second draw the tangent line. What would the slope of the tangent line at 1 second be? So if I ask you, what's the slope of the position time graph at a particular time? That's the magic code for, oh, how fast is it going? Okay, so there's two ways I can ask you how fast something is going at a particular point in time. I could just say straight up, hey, how fast is it going after 1 second? Oh, 3.9. Or I could say, hey, what's the slope of the position time graph? Oh, that's the slope of the position time graph, gives you your instantaneous velocity. That's another way of asking how fast it's going. Okay? Does that make sense? So those are the two ways I can ask you. The slope of the position time graph, or I could say how fast it's going. Now, to figure out how high it is, there's only one way you can do this. Okay, that's at all relatively simple. The only thing you can do, and this is like a function equation, okay? The only way you can do that to figure out how high it is to use this, plug in 1 second squared plus 13.7. Now, before you do any calculations, at 1 second, should my position be a positive or negative value? Positive, right? It hasn't reached its maximum height. So I know my maximum, what do we get as a maximum height? 9.6? So at 1 second, I know my answer has to be less than 9.6 meters because I haven't reached my maximum height yet. If I get an answer bigger than 9.6, I know I've done something wrong. If I get a negative value out of this, I've done something wrong. Because I'm not going to throw this ball up in the air and then at 1 second have a negative position, which would means it would be below where I launched it, which would just be really weird. So, Matt, what do you get?
8.82.
8 point what?
82.
Okay? So that means it's pretty close to being towards that peak. We're not there, but it's pretty close, right? Okay? Now, the only thing left, if we're going to do this at 2 seconds, the only thing that's going to happen at 2 seconds is that we're going to use this exact same equation. The only thing that's going to be different is that we're going to plug in 2 seconds here. Now, Matt, do this. Take negative 9.8 times 2 and add that to 13.7.
Negative 5.88.
Now, notice that this velocity is negative. Oh, it started on its way back down. Okay? Because we hit a maximum height at 1.4 at 2 seconds we're on our way down. My velocity vectors are now pointing down. I've got a negative velocity. Now, at 2 seconds, is my position going to be a negative value? Matt, you shake your head no. Why?
You're still above your ground.
Yeah, I'm still above the ground. I'm going to have a negative velocity, but I'm still above the ground. So the only thing that you're going to do is you're going to plug in 2 seconds here. You're going to get a number. Okay? Got it? Good? Grand? All right. I'm done.
I just got like,
You okay?
yeah, it's just, sometimes when I run, I get like a little, like congestion. And I just have to put it,
Okay.
Maybe
All right.
why is that why is that, balloon named Cheryl?
Because my 4th block AP class decided to name Cheryl.
I don't know why I got confused with balloon and Cheryl. I mean, hello.
Yeah, that one's Cheryl,
Wave the
and
rock.
I can't remember what the name of that one.
You draw the rock? I don't
So-
draw the pictures.
Oh, you want to
Draw
do
the
a kangaroo?
arrows.
Okay, now let me kind of get you started on this, and then I'll turn you loose. So the first part, this is kind of the review for the test. Okay, when you get to number 4, it says you're going to throw a ball up in the air, and it lands 4.40 seconds later. So all of number 4 is like the problem that we just worked. The only difference is that instead of using 2.80 seconds for the total time, you're going to use 4.40 seconds. Okay? Now, if your answer to 4A is wrong, everything is going to be wrong. So your answer to 4A should be in the low 20s. Okay? So your answer to 4A should be in the low 20s. Because if that's wrong, everything else is going to be wrong. Now, so you're going to end up drawing a whole bunch of graphs. I'm going to give you some graph papers you don't have. So you're going to draw a position time graph that oddly enough is going to look like the one that you all just drew. It's going to look like this. Okay, it's just going to be a sketch. Okay, but you are going to know the maximum height at that point. So now what I'm asking you is that what will the slope of the line be at time 0? You don't actually have to draw the tangent lines. All I'm asking you for, and here's the magic code, is that, well, how fast is it going at time 0? What would the slope of that tangent line be at time 0? That's what I'm asking you. Basically, all I want you to do is figure out how fast it's going at different points on the graph, which would be the slope of the tangent lines at those points. Okay? All right. Now, when you get to question number 8, so let me kind of paint what's happening on number 8. You have 2 spaceships, Enterprise, and then you have Columbia. So they're at the same point at time, and the Enterprise is going 450 meters per second, Columbia is going 600 meters per second. So here's what's going to happen. They're both going in the same direction at the same time, and they're at the same point. They're going to go out, they're going to stop, and then they're going to come back, and they're going to end up back at the same point 86 seconds later. Okay? So they're here, they're going to go out, and then they're going to come back. Okay? So 86 seconds later, they both end up back at the same point. So did they both change directions? Yes. Did they both accelerate? Yes. Okay? So keep that in mind. So you're going to draw a velocity time graph showing the motion of each of these on the same graph. So that's going to be the third one. So your first graph is a position time graph for the ball. The second graph is a velocity time graph for the ball, which is going to look something like this. Okay? The third graph is going to be a velocity time graph for Columbian Enterprise. You're going to put both of them on the same graph. Now, when you get to number 9, okay, and I promise you there's going to be a problem like number 9 on the test. Okay? So here's what's happening on number 9. So here's a rocket. Now, what's going to be different about this one is that we're going to start this at 0. Okay? We're going to start this thing at 0. Your velocity time graph, listen to me, is going to start at 0. Okay? So here's what's going to happen. I'm going to fire this rocket, and it's going to be going, after it goes up in the air, it's going to be going 30 meters per second when it's 25 meters above the ground. Okay? You're going to start at 0. Okay, so here's your rocket. Okay, it's going to fire it up. Okay, and you're going to go to 30 meters per second when it's 25 meters above the ground. So you want to determine the acceleration and draw motion diagrams to show the velocity vectors and the acceleration vectors. So obviously, you're going to start at 0 and you're going to end up going 30 meters per second. So on the way up, are your velocity vectors getting bigger or smaller? Bigger. So what's the direction of my acceleration vector?
Up.
Yeah, because my velocity vectors are getting bigger, right? So my acceleration vector is going to be pointing upward. Now, at that point, I shut off the engines. And this goes back to this Jedi stove law. Stop the force and watch. So, while the engines are firing, that's like me holding this ball in the hand, and I'm throwing it up in the air. Now, as soon as it leaves my hand, or as soon as this rocket shuts off the engine, what's the only force acting on it? Gravity. And what's going to be the acceleration due to gravity? Negative 9.8 meters per second squared. So you're going to have a positive acceleration while the engines are being fired, and then you're going to shut off the engines, and then it's going to coast to a stop. Okay? So, on number 10, here's going to be the next one. Okay, here's going to be your fourth graph. You're going to draw a velocity time graph, and here's what you want to do. You want to keep like a running clock. So what's going to happen on number 10, your velocity time graph, if you do this right, is going to go something like this. Okay, should be like a slanting triangle. So this is when you're firing the engines and you're speeding up. This is when you shut off the engines, and now it's going to coast to a stop and go to that maximum height. Okay? Keep that in mind. Now, the mini lab on the last page. What your task is going to do is you're going to try and find an experimental value due to gravity. Okay? So listen to me. On the mini lab, listen to me. Do not use negative 9.8 meters per second squared as your acceleration. You're trying to find an experimental value of the acceleration. Okay? So do not on the mini lab. You can use it on the beginnings of the lab. Okay? Up at page 1 and 2, you can use negative 9.8. Don't use it on this one. The only time you're going to use negative 9.8 is when you get down there and you're going to calculate the experimental error. Okay, remember your experimental error is theoretical minus experimental over theoretical. It's on your equation sheet. Okay, watch the negative signs. So here's what you're going to do. You're going to have Kara bounce the golf ball. Okay, you're just going to use this golf ball. And you want to bounce it like that. So you want to have a couple people timing it from bounce to bounce. Okay, right? From as soon as it hits the ground to the point that it comes back. Now, the tricky part is that you also have to have set up like maybe a couple meter sticks or something, and you also have to measure the height that the ball goes to. Okay? So this is going to require a little bit of teamwork amongst the four of you. So you got to have somebody bouncing it, and then somebody recording the maximum height, and somebody recording the time from bounce to bounce. Okay? So what's going to happen is that your position time graph, oddly enough, is going to look something like this. We're making the ground the reference point. Your velocity time graph is going to look something like this. Okay? Now, what you're searching for, this is a kick back to the very first lab that you all did in this unit, where you pushed it up the inclined plane, okay, and you used the area of a triangle, and you found that height. So what you're going to know is you're going to know the displacement on the way up. You're going to know your final velocity is going to be 0. You're going to know how long it's going to take to go up. Then you can find the initial velocity, and then you can find the slope of the line, which is going to be your experimental value of acceleration. Now, I'm telling you, make sure in big bold letters, I tell you, show every step of every calculation. I refuse to guess what you have done. Okay? So, on here, you're going to have calculations on the way up, calculations on the way down. You're going to draw a position time graph and a velocity time graph. So you're going to end up with 6 graphs. And you don't have to draw like a full page graph for each one of these. You can divide and conquer, because these are just like these are just sketches of graphs. Okay, I'm done. So make sure I get that assignment. Yes?
If it's a position time graph and it bounces twice, why wouldn't there be like 2 of those?
No, because we're going to start it from where it hits the ground to when it comes back to the ground.
Oh, okay.
Okay, so we're not including Kara throwing it.
Okay.
So we're just going to go like this is this instant that it leaves the ground. This is this instant when it gets back to the ground. Okay?
That makes more sense.
Yeah. So yeah, it's just here to here. And we're not going to include Kara throwing the ball down. We're just going to start it from the instant that ball leaves the ground to when it gets back to the ground. Okay? Now, if you want to use your phones and stopwatches, if you really wanted to get fancy, you could have someone, if your phone has slow motion, you could like record the ball with the backdrop of the meter stick, and that way you could get the exact height if you wanted to do that in slow motion. That's just an option. You don't have to. It's just how techie and nerdy you want to get. So, all right, I'm done. You're on your own. There is yonder golf ball. Oh, good catch.
My ankle hurt.
Oh, I keep it down. This thing right there. No good.
Now, some people would like to measure the height of the ceiling. Some people would take meter sticks along the wall. You all figured it out.